structure of the atom. If you haven't quite finished the questions, then you can finish them off once I've finished talking. So we're looking at page 8. And you can see on that diagram on the top of the page, or leftish of the page, you can see the different kinds of thinking, the evolution of our understanding of the atom over time, where Dalton was using, if you like, almost an ancient Greek, the atomos kind of thinking of the atom being the smallest reproducible part of an element. Then with experimentation, we discovered that that's not right, and the discovery of the electron. And then we've got Rutherford's very famous experiment where he's firing alpha particles at a very thin sheet of gold. Okay, so the thinnest sheet of gold that he could make, and he chose gold because it's quite malleable. You can hammer it very, very thin. And what did he see? But sometimes these particles came back, like bounced straight back, and others went straight through. And it was so surprising. He said it was like firing a cannonball at a sheet of paper and having the cannonball bounce back. That's how unexpected it was. What was doing this? What was the reason for this? And the reason was there's a nucleus. Didn't know about a nucleus before that. Because all the vast majority of the mass of the atom is in the nucleus there. And that is why it could bounce back that alpha particle. Then with a bit more experimentation, Bohr, probably he's definitely in my top 3 favourite scientists of all time. His development there of the levels of energy for electrons. So he was examining spectra, and you could see the bands of line of colour that were being emitted when he excited these atoms, and this is where we understood that the electrons were sitting in stable energy levels. And of course, Bohr's model didn't actually stand up for very long because they don't actually do that. It was great thinking, it was really good. But with further analysis with Schrödinger and Heisenberg, etc., we end up with the quantum model of the atom, which we look at in chemistry, but we use the Bohr model for physical sciences. Okay, so because it's close enough, it's a reasonable approximation for us to use in this introductory level. As it says here, the nucleus is where most of the mass is found in an atom, and the nucleus then is made up of protons that are positively charged and neutrons that have no charge. Yeah, so hopefully this is all just revision. And then a long way out, actually like way, way, way out, is where the electrons are. Now for this to be an atom, which has got a very wonky, but never mind, I've got 2 protons in my nucleus. For this to represent the atom, I have to have 2 electrons. Because in an atom it is electrically neutral, which means that my positive charges in the nucleus are balanced by the number of negatively charged electrons I have orbiting the nucleus. Protons and neutrons are virtually identical in mass and carry the mass, most of the mass of the atom. You can see here for the electron, its mass relative to a proton is 1 divided by 1,836, which is a very small number, so it's negligible. But it's, even though it has nearly no mass, its charge is equivalent to the charge on a proton. All right? And yeah, we knew about electrons back in Thomson, and electrons are important for chemistry because this is where the chemical reactions take place.
So that's why electrons are. What about neutrons? Like, what's the point of their existence? Like, they're literally just there and doing nothing but add weight.
You'd think that they're there and doing nothing, but they have an important job because like charges repel each other, and you wouldn't be able to get a very large nucleus occur without the neutrons separating the protons from each other. And so that's their job, is to stabilise the nucleus.
So it's space.
And they like, even though mine look a bit dodgy, like the whole diagram is dodgy, let's face it, but there is actually stable arrangements of the neutrons in relation to the protons to keep the nucleus stable. Yeah, so they, and all of those on that old periodic table where there were no elements listed, but they now are named and they have been manufactured for very short periods of time. Some of them are very, very unstable. But in order to make them at all, they had to know how many neutrons that they needed in there. Okay, because and there's if you go on to do physics, then that would be a calculation that you'd be able to do to determine whether the number of neutrons present means that that atom is stable or not. Okay, so if we look on page 9, we can see then that all atoms, as I said, are electrically neutral, which means that the number of electrons is equal to the number of protons present, so that they cancel each other out. All atoms of the same element contain the same number of protons and electrons. Notice that it didn't say neutrons. Okay, so each element will have a defining number of protons. If it's in its elemental state, then it will have this matching number of electrons. But the neutrons are a separate story. The number of protons in the nucleus is called the atomic number, which is given the symbol Z. And the atomic mass of an atom is the number of protons plus the number of neutrons. So my atomic number for this diagram here would be 2, wouldn't it? Because, which would make it helium. And Z is 2, and whereas my mass, A, would equal 4. Yep. And ions. We were talking about ions a little bit over at this table before. As we said, this is an atom at the moment because the number of electrons match up with the number of protons. If I lose an electron, then I don't have the same number of protons and electrons anymore. And in this case, I've lost an electron, and so I've got an excess of positive charge. This is then an ion. Okay, this would be an ion with a +1 charge because I've got 2 protons and 1 electron. It means I've got 1 extra positive charge. Does that make sense?
Is that the cation?
And we can call this a cation. So all cations have a positive charge. And an anion is a negative charge, which would mean I have more electrons than protons. when we look at our periodic table and we look at our masses, they're not just integers, they're not whole numbers. We see numbers as so for chlorine, its relative atomic mass is 35.45. It's not an integer, and that is because there are isotopes of these different elements, and the isotopes are because there are different numbers of neutrons in the nucleus, changing the mass. It doesn't change the element because we know the element has a certain number of protons. But if we change the number of neutrons in the nucleus, we change the mass. Okay? And we can, each different kind of atom is called an isotope. Now if we looked specifically at carbon, so if I use the atomic notation, you can see here that this is the mass, and it is made up of protons plus neutrons, and this is the atomic number, which is just the protons. This is one isotope of carbon. A very common isotope of carbon is carbon-12. Okay, and so if this bottom number is telling me how many protons I have, carbon-14 must always have 6 protons. If I don't have 6 protons, it's not carbon. But because this one, carbon-14, has a mass of 14, then it must have 8 neutrons. Because 6 plus 8 equals 14. With my carbon-12, it also has 6 protons. But with an atomic mass of 12, then it's going to have 6 neutrons, because they add up to 12. And I could also have carbon-13, which again has 6 protons. How many neutrons? 7. If I were talking about atoms for each of these isotopes, okay, so these then are called isotopes of carbon. If these were all atoms, how many electrons would be present? Yes, because it's electrically neutral to be an atom. It has to have the same number of electrons as protons. Okay. I'll get you to do the questions on page 11, questions 9 and 10. Get the later. Fired up.